10 deals with differentials. And you can say again, yes, it's the same topic, absolutely the same. Just different applications now. Differentials and linear approximations. Differentials and linear approximations. So let's go back and refresh our memory on differentials. This is what we did last time. I just want to show you again how powerful that result is. You will not even believe what you can do with that result. Okay, so remember what we did. We looked at one of our best friends, the function f of x, and we had p with x, of course, f of x. We had q very, very close, x plus dx, and of course, f of x plus dx. And we analyzed this, and we knew, if we realized that, we learned that this is the exact change, which is f of x plus dx minus f of x. All the same from last time. But this time we said, okay, is there a way of approximating this exact change? And here there is the way. We drew the tangent at P. We created a right triangle. And we said that if this is dx, and the slope of this line is f prime of x, that's the slope, then we know that this must be only one thing. What can it be? Because the slope of this line must be this over this, which must equal f prime of x. So then what could this be? Exactly. And since P and Q are so close to each other, so this was Q, they're so close to each other, delta y, the exact change, the exact change will be very, very close to the estimated value obtained using the derivative. The first quantity on the left, the exact change, is not determined with the derivative. This side is determined with the derivative. So now I will copy this here, and I will copy what dy is equal to. So this is f of x plus dx minus f of x is approximately f prime of x dx. And therefore, I will move f of x to the other side. This is exactly what we did last time, nothing new for now. Very powerful result. We already looked at this result with estimating the area of the disk when an error occurred in the radius of the disk. But now I just want to show you something that you would probably, again, have never thought of. This relationship will allow us to estimate almost everything you can think of that you normally would not be able to do without a calculator. So here's an example that I like to start with. 23, 24, 25, 26, 27, 28, please choose. So let me read those problems to you. Are you interested in estimating 1.999 to the fourth power? Are you interested in estimating e raised to negative 0.015 or any of these? You will be able to estimate without a calculator.
26.
Okay, we want to start with 26. Very good. 26, and it's a very good pick, and I want to start with 26. But then eventually I still would like to show this, because this one is mind-boggling. Who do you think is able to estimate e to negative 0.015? If they don't know this, I doubt. Without a calculator. Okay, so we decided to start with 26. So it's 1 over 4.002. So all we have to do is apply this result. And you can say, how do I apply this result? Very simple. I have to identify f of x. I have to identify x. I have to identify the error, or dx. And of course, once I have f of x, I will find f prime of x. So that's all I need. I need f of x, I need x, I need dx, and then I will differentiate. Good. So look at this and tell me which function is used here. Which function is used here? Okay, it's too big. Which function is used here? Of course, absolutely, 1 over x. Good. What is the derivative of 1 over x? We made a deal some time ago saying we will remember the derivative of 1 over x. So we don't have to put x to -1, bring the -1 in front, subtract 1 from the power, and then go back to a fraction again. But it's okay. With minus. Excellent. Good. Good job. Now I have to identify x and the error. So what would you pick as x? And what would you pick as the error? Remember, the error has to be tiny, and x can be anything. So what is x? Exactly. And what is the error? Very good. Very good. Indeed. So I identified everything. This is this. This is the same thing with f of x plus dx. And now we are going to approximate it. Please dictate. And I will write it. F of x. Very good. Excellent. Plus. Very good. Careful. X is 4. Good. Multiplied by? That's it. Yes, it needs a little bit of simplification, but that's it. So this is 1 over 4 minus 0.002 divided by 16. I will multiply top and bottom by 1,000 to eliminate decimal numbers. I'll simplify by 2. I'll multiply this by 2,000. 2,000 minus 1 is 1999 over 8,000. And now let's see if this is a good approximation that we can live with or not. It's not exact. It cannot be. It's an approximation. Ready? So let's plug in 1 over 4.002 and plug in 1,999 over 8,000. To see the difference. There must be a difference. But let's see about how big it is. Okay, 1 divided by 4.002 and 1,999 divided by 8,000. Pretty good? It's not exact. We don't expect it to be exact, but it's pretty good. Okay, so now let's do that E thing. Because this one is not that surprising, right? I mean, not a big deal. I can divide. But this is absolutely impossible by hand. So let's take a look at 24 on 255. So this was 26 on 255, my apologies. And that is E to negative 0.00, I think it is, yes. No, just 10, 15. 0.015. Okay. I'm going to copy our result, the very powerful result. And you're going to find for me f of x, immediately f prime, x, and dx. Once we are able to identify these quantities, the problem is solved. F of x. Very good. F prime. Of course. X. I have to identify x, and I have to identify the error.
0.
Exactly. Excellent. And what is the error?
0.015.
Yes, but negative. Excellent. Great job. Everything else is a piece of cake. So now I can write the equal symbol from here, or you can write e to negative 0.015 is approximately, because that's what this represents. F of x plus dx is exactly e to what I'm trying to estimate. Good. So can anyone dictate the left-hand side? Don't calculate for everyone to see, so let's plug it in.
So left-hand side.
Yes, the left, no, I meant the right-hand side. I did say the left-hand side, I think. Yeah, sorry.
So EX
E to the,
E to 0.
good, plus
E to 0.
e to 0 times,
X negative 0.015.
good. How much is e to 0? Good. How much is 1 times this? So this is 0.985, right? Good. Would you have believed that you're able to evaluate, estimate, I should say, not evaluate, estimate, e to negative 0.015?
Is it not 2? E to 0 plus E to 0?
But I cannot add before I multiply. By the order of operations, I have to multiply first and then add.
Okay.
Is that okay, everyone? Okay. Good, so let's plug it in. So we have E in parentheses negative 0.015. Pretty good? We got 0.985. And this is 0.9851, blah, blah, blah. Pretty good, isn't it? Okay. Any questions about differentials and estimating using differentials? Okay, before we look at other problems, I'd like to go back to linear approximations. I have not discussed linear approximations. We have not done anything with that. So let's go back to our best friend from day one. Of course, P, A, and what is this? This is point P, X is A, and then, perfect, thank you very much. Good. I'm going to draw a tangent line. I want the equation of the tangent at P. How do I determine the equation of this tangent at P? I need two things. I need the point and I need the slope. And then I'm in business. I can determine the equation of the tangent. Okay, do I have the slope? Do I have the slope of the tangent at P?
Function of A over A.
Say it again.
Function of A over A.
You mean f prime of A?
Oh.
Perfect. Yep. Right? The slope of the tangent line to the graph of the function at P must be f prime of A. Agreed? Everyone? Perfect. Okay, so then I have the point and I have the slope. I can determine the equation of the line. Y minus y1 equals the slope times x minus x1, where a is x1, f of a is y1, and this is f prime of a. So I have everything. So far, so good? Okay, so then now I write f minus f of a equals f prime of a times x minus a. You can see, but this is exactly the same thing you did a few minutes ago, pretty much. I'm going to move f of a to the other side. And this looks very, very similar, and it is very similar to our previous result. I hope you agree. I'm going to show it to you once I get to it. But it's the equal symbol now. Okay, what does this represent though? And what does this mean? Okay, I'm going to graph it again. I don't want to go back. Okay, so here is our graph. Here's our function. It was P. This line has the equation y equals f of a plus f prime of a x minus a. You're going to see this again in Taylor series in Calc 2. Okay, so what is this all about? It says this. Any function can be approximated by a line, by the equation of a line. What do you mean? Yes. So if we are interested in evaluating this function very close to a, not here, but very close to a, it doesn't really matter if you use the function or if you use the equation of the tangent line. Will you have an error if you use the tangent line? Of course. But it's going to be very close, like we just saw, 0.985 versus 0.98511, right? So that's what the equation of the tangent line shows, right? So if I use this equation, or if I use this function, when I evaluate close to A, I'm going to get something very close. If I want to evaluate something close to B, then I have to create a new equation. I would have to use the tangent here. This will be a totally different equation than this one. And I could use this equation of the line, of the tangent line, to evaluate the function at B, instead of using the function itself. So any function can be approximated by a line. Of course, a different line for different points. Not the same line at every point, but it can always be approximated by a line near a point. So this, as a function, is called f of a plus f prime of a times x minus a, is called the linearization. Of f of x. Very important word. If you move away from a, then you're not going to be able to use the same equation. We have to create another equation. Okay, let's practice this, and I would like you to choose. Find the linearization L of x of the function at a. Please choose any function you'd like, so we can practice this. Find the linearization L of x of the function at a.
Number one.
Number one, very good. So we want to look at number one. On page 255, we're given the function f of x, which is x to the fourth plus 3x squared, and a equals -1. Good. So the linearization is f of a plus f prime of a times x minus a. That's another important result, but it's the same with the previous result, but just different notation. Okay, so I have to determine f prime of x because I eventually need to determine f prime of a. I know that this becomes x plus 1, so I have to find f of -1 and f prime of -1. So first let's find f prime of x. What does f prime of x equal to?
4x.
To the third, very good, plus
6x.
that's it. Awesome. So now we want to find, we are preparing, we are just doing the prep right now. We plug in -1, so this is -6 and this is -4. When we plug in -1. So we get -10. Agreed? Okay, so now the linearization will be f of a. We did not do f of a, so f of a will be 1 plus 3, which is 4. We agree with L of f of -1 as being 1 plus 3 equals 4. Yes? Okay, so then I have to copy f of -1, which is 4, plus f prime of a, which is -10 in this case, and then x plus 1. As expected, it's a linear function, it has to be. So -10x minus 10 and plus 4, -10x minus 6. So what does this say? It says that if you want to evaluate this function near -1, it's okay to use this line. So the function, I'm going to copy it here so I don't have to go back there, is this. So if you want to evaluate, let's say this function, again, this is near, this is near -1. So if you want to evaluate this function for -1.1, and you're happy with some minor error, you will not use this. You will plug it in here. -10 times -1.1 will be +11. +11 minus 6 will be 5. Yes, 5. Quick, because a linear function is much easier to evaluate than any other function. But it has to be near -1. This function will not, this linear function will not help us evaluate at any other point, but very, very close to -1. Now, if you want and you change a and you say, no, I don't want a to be -1, I want a to be 10, then you will create a new function, a new linear function with 10 in here, f of 10 and f prime of 10, and this will change. But I didn't have to go through -1.1 to the fourth power and plus 3 times -1.1 to the second power. I use the line and I determine the estimate quite fast. Because the linear function is the easiest to work with. Any questions so far? Any questions? Okay, so I would like us to choose, before we look at another word problem, I would like us to choose anything from here. Let me show you what they are asking us to determine. So they're given the function and they want to find the differential. We have to pick one problem from here. Then again, the same thing, find the differential and evaluate the dy for the given values. That's fine. I mean, one from here is good enough. And then compute delta y. I would like to choose one from here. One from here, one from here. Compute delta y and dy for the given values. So one from 11 to 14 and one from 19 to 22. You choose.
21 is a lucky number.
20 was a lucky number. We'll do 20. And what about here? 21. Sorry, 21. 21 is even better. Sorry. 21. Perfect. And from here, part A or B, doesn't matter. Just one.
I'll lose that. Oh.
So this is part A, part B, part A, part B. They're not connected.
Reverse at 12.
We want to do 12. So 12 and 21. Excellent. Well done. Maybe we'll win something. Next time I play the lottery, I'm going to do that. How did you come up with reverse? Is there any thought behind it or just?
I just like 21, so 12 is just
Very good.
numbers in reverse.
That's it. 21 and 12. Excellent. Part A or B? I'm sorry, I forgot to ask. Part A or B? In 12.
B.
B. Perfect. Okay, so this is 12b, and we have y equals e to a negative u cosine u. I think it's, yes, that's correct. Good. So remember, there are two different situations. One situation, which is this, in this case, u, and this, which is a totally different situation, which is f prime of u times du. So this is the derivative, and this is the differential. The derivative is one thing, the differential is f prime of u du. Okay, so this, we're not asked to find this, we're asked to find this. I see a product in there of two different functions. So I have to differentiate using the product rule. Ready? So dy would be I need to have a sum of two different terms because it's a product, and the product rule requires us to write two sums. Let's differentiate the first function. What do we get?
E negative u cosine u
Times the inner function prime.
times
The inner function prime. Exactly. So negative e to negative u times cosine u. E to negative u times.
negative sine.
Excellent. This, we're going to clean it up a little bit by factoring out negative e to negative u. But this is the differential of function y. So dy equals negative e to negative u, and in parentheses, sine u plus cosine u in the correct order. This is it. So this is the differential. Extremely important topic for the last chapter in this course, chapter 5. This is the differential of a function, which is f prime, the function prime, times dx. Any questions on the differential? So please remember the difference between the two. The derivative is not the differential is not the derivative. And we are looking at 21. In 21, we are given y equals 2 over x. We are given x equals 4. We are given delta x, which we know equals dx equals 1. They're asking us to compute delta y and dy. So let's read the problem. compute delta y and dy, the exact change and the estimated change, for the given values of x and dx equals delta x. Okay? Let's start with the easy one. We know that this is dy equals f prime of x dx. And that is always the easy one. So y is 2 over x. If we remember that this is 2, or if we see it as 2 times 1 over x, then we're going to be able to differentiate it very fast. And if we also remember that 1 over x prime is excellent, we are done, right? So dy is negative 2 over x squared dx. All I have to do now is plug in the numbers that I was given. So then dy equals negative 2 over 4 squared, which is 16, times dx, which is 1. So the answer is negative 1 over 8. And that was dy. And that's the easy part. Delta y, because of 4 and 1, is not going to be difficult. But if I had 4 and 0.001, it would have been a little bit more complicated because of the numbers. Delta y is f of x plus dx, but minus f of x. And this is the exact change. The exact change triggered by 1, dx, 1, in the function. So that will become, since x is 4 and dx is 1, this will be f of 5 minus f of 4. Not a big deal. 2 over 5 minus 2 over 4. I don't recommend simplifying. We can simplify. Normally I would say 1/2, but still I have to multiply the denominators. So it's 20. 4 here and 5 here. 4 times 2 is 8 minus 10, negative 2. So negative 1/10. Are they close enough? Dx is not a small number. Dx is 1. So negative 1 over 8 and negative 1 over 10, not as close as I wanted them to be, but because the error is big. The error is a quarter, right? A quarter of 4. The error is quite big. So this is the exact, and this is the approximate, the estimated. Which is bigger, right? Okay. Let's look at a word problem and then we can close this section. And I have a few minutes to show you 3 more functions. Okay, so let's look at a word problem. I remember we did this, last time. I'm sorry. The radius of a circular disk is given as 24 with a maximum error, and we use differentials and so on and so forth. Let's choose the next one. Or something else. The edge of a cube. Yeah, let's look at the edge of a cube. I don't think I've ever looked at that one. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume and the surface area. So the edge of a cube was found to be 30 centimeters. What does that mean to us? From all the pieces that we looked at, what will that represent, 30 centimeters?
X.
Excellent. Thank you. That's X. With a possible error in measurement of 0.1. From everything that we looked at today, what could 0.1 represent?
Dx.
Of course. Use differentials to estimate the maximum possible error, relative error, and percent in volume. So we draw a little figure. Excellent. We're basically doing the same thing. We're trying to estimate this error. But this time we have x, which is the length of a side of a cube, and we have the error. So that's exactly what we're doing, but in a word problem. All the same. So this is problem 33 on 255. And here's our cube. And this is x everywhere. So let's write the volume and let's write this total surface area before we put in everything else. So what is the volume of this cube? And everything is measured in centimeters. Indeed. And what about the surface area of the cube?
X squared.
Times 1, 2, 3, 4, 5, 6. Good. Very good. So now you already identified, you said that x is 30 centimeters. You already told me that the x equals 0.1. So now we have two tasks: to estimate the error in the volume and estimate the error in the surface area. So let's start with the volume, because we have actually 3 questions for each. Volume. So let's see what we are asked to determine. It says use differentials to estimate the maximum area. Maximum error in the volume, and then number 2, area. So how do I determine or estimate the maximum possible error?
F prime actually X.
Yes, exactly. But we are using v. Excellent, yes. So this will be v prime times dx. Great job. So dv will be 3x squared dx. All I have to do is just punch in the numbers. So dv equals 3 times 30 and times 0.1. So 0.1 times 30 is 3, 3 times 3 is 9. Measurement unit.
Centimeters cubed.
Excellent. Great job. So an error of tiny error of 0.1 centimeters will trigger a 9 cubic centimeters error in the volume, maximum estimated value. Okay, so let's do the same thing here. dA equals a prime dx. So then dA will be
Will be 12x.
very good. So dA will be 12 times 30 times 0.1. Again, this is 36. Measurement unit.
Centimeters squared.
Very good. So this is the max error estimated. Max estimated error. We're also asked to determine the relative error. So let's talk about relative error now. For both. The relative error is equals the error divided by original. I'm not going to put numbers at the beginning. I just want you to see what happens here. And then we can put the numbers in. So the relative error for the volume will be the error, which is 3x squared, so dv over v. The error over the original. Original is the volume. So dv, we already have it, is 3x squared dx. And the volume we have it is x cubed. I want to simplify before I plug in the numbers. So you see, you'll simplify by 2 x's from the top and 2 x's from the denominator, and 1 is left. Or better written as 3 times dx over x. Why? Because this represents 3 times the relative error in x. Because there is an error in x, and this is the relative error. So that's okay. So now I have 3, and then I have 0.1, and then I have divided by 30, and this will be 0.1 divided by 10. I simplify, and this is 0.01. This does not have a measurement unit. Why? Because the error in the volume is in cubic centimeters. The volume itself is in cubic centimeters, so there is no measurement unit for the relative error. We're also asked to find the percentage error. All I have to do is just change this into percent. So this is the percentage error. Similarly for the other one, for the area, same thing. It's dA over A. It's 12x dx over 6x squared. I simplify in the same way, and this time this is twice the error, the relative error in x. Plug in the same numbers. I have 2, I have 0.1, I have 30. So this is 0.1 over 15. Again, with no measurement unit. Why? Because the numerator is measured in centimeters squared and the denominator is centimeters squared. So 0.1 divided by 15 gives us 0.0067. So this is approximately 0.0067, and in percent will be 0.67%. That's the percentage error. So the relative error will be 3 times the relative error in x. The relative error for the area, this was for the volume, will be twice the relative error in x. No measurement unit, because both are measured in the same and they cancel out. The measurement units cancel out. The last thing, I know I have like 8 minutes left. The last thing I wanted to show you, 3 more functions. You can say, don't we have enough? No, I'll show you why we don't have enough. So this is the last section of this chapter. I'm only asking you to do, remember the 3 functions and their derivatives, not their inverses, not the derivatives of the inverses, just these 3 functions. They are called hyperbolic functions. They are not trig functions. However, they are called hyperbolic sine, hyperbolic cosine, and hyperbolic tangent, but they're not trig functions. So first of all, let's define them. Just 3. There are 6, of course. Hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. They are combinations of exponential functions. So they're e to x minus e to negative x over 2. Cosine is identical but with plus. E to the x plus e to negative x divided by 2. And yes, of course, tangent is the ratio of the top ones. E to the x minus e to negative x over e to the x plus e to negative x. So they are combinations of exponential functions. And I want to show you a couple of real-life situations when they could not fit anything. Not a polynomial function, not a rational function, not a trig function, not a log function, nothing. But a combo of exponential functions. First combo called hyperbolic sine, the second one hyperbolic cosine, and the last one hyperbolic tangent. So here it is. This is a very typical example. So what is this? So you can say, well, we don't use telephone poles like that anymore. We don't. Everything is on the ground. So what are you talking about? Well, they're still used somewhere. So they needed to determine the length of this arc, if you want, between the two poles. Nothing worked but the hyperbolic cosine. The same thing, to model the ocean waves, same. I have not been to St. Louis, but this is kind of famous, this arch. Yes, it was determined and built. The architect used a function that was a combo of hyperbolic functions. Okay, it's a hyperbolic cosine function. Nothing worked. You know, for him to build this or work on the project, that he had to use a hyperbolic cosine function to build it like that. Because he needed measurements of everything, opening, height, etc., etc. So now the derivatives of these functions, very simple, identical to the trig functions and no negative signs. So when you differentiate hyperbolic sine, you get hyperbolic cosine. And also when you differentiate hyperbolic cosine, you also get positive. Do not confuse those functions. We normally get for trig functions, we get negative, right? But not here. And the last one, what do you think? Just a wild guess for hyperbolic tangent prime. Yes, you're right. What do you think?
Has the hyperbolic sine and the hyperbolic cosine.
Exactly the same. So hyperbolic sine prime is hyperbolic cosine prime is hyperbolic sine, and hyperbolic tangent, of course, is hyperbolic secant squared. Okay, I would like us to choose an example. So here's that example again. Okay, so I would like us to practice anything from here with those three functions. You don't have to worry about hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. Sorry. Anything you like to differentiate. 31, perfect. So let's look at 31 and then we'll stop. On page 263, and this is the end of chapter 3. So 31, I see it. So f of x equals x times hyperbolic sine minus hyperbolic cosine. So we only are asked to find f prime. I would also like to look at 35. Promise, this is it. I'm already shutting the book. E2 hyperbolic 3x. I think it's 3x. Yes. Okay, so this is a product, careful. So I have to write a sum of two terms. X prime is 1 hyperbolic sine plus x times hyperbolic, yes, I differentiate sine to write hyperbolic cosine x. And here minus hyperbolic sine, would you agree? It happens that these two will go away and the final answer is nice in a product x hyperbolic cosine x. And the last one, y prime or dy over dx. Can anyone give us the answer? So it's e to a function prime. So I have to write e to hyperbolic cosine 3x times, yes, hyperbolic sine 3x times times 3. You can rewrite it, but that's it. We cannot do anything else. So e2 hyperbolic cosine 3x times sine hyperbolic sine 3x. This is it. So just remember that hyperbolic functions are combos of